Hello everyone, welcome to the course on computer networks. Today's topic of discussion is error correction. That is, we are going to have a discussion on the Hamming codes. Myself, Mr. Ankit Khandelwal, Assistant Professor from the Department of Faculty of Computer Engineering, Purnima University. The content of this lecture are as follows. First of all, we will see why the error correction is needed. Then we will see the Hamming code, how this Hamming code can be used for detecting the single bit and how it can be corrected. Then we will see with an example of Hamming code with the conclusion, and then in the last there are references. The objective of this lecture is to understand the concept of error detection and correction in digital communication, to learn how Hamming code is used to detect and correct single bit errors, to explore the process of encoding and decoding using Hamming code, and to apply Hamming code for reliable data transmission in computing and networking. After seeing this lecture, the student will be able to explain the importance of error correction in the communication system, can use to implement Hamming code to detect and correct single bit errors. They will be able to analyze the working of parity bits in error detection, and will be able to apply error correction techniques in real world applications such as computer memory and digital networks. So error correction can be handled in two ways. First, the receiver can have the sender retransmit the entire data unit. And second, the receiver can use an error correction code which automatically corrects certain errors. Now, we know that when we are going to transmit the data from sender to the receiver, okay, to the receiver. This is the data which we are transmitting. Then in between, when going from sender to receiver, this data may be corrupted. So here we are going to discuss that we are having a error in a single bit. So let us suppose this was the actual data which has to be transmitted, and the received data is this one. So here is a single bit error. So first of all, receiver has to detect this error. Fine. Detect the error, and then we'll use some techniques to detect this error. These techniques are, that is, VRC, vertical redundancy check. Second, LRC, that is longitudinal redundancy check. Third is checksum. And the fourth one is that is CRC. So using these four techniques, the receiver can detect the error. Now, if receiver finds an error in the data, then it can be handled in two ways. That is, the receiver can have the sender retransmit the data. So here in this, we are talking about for the retransmission of the data. So for retransmission, we use automatic repeat request algorithm, right? Automatic repeat request algorithm. In that, we have stop and wait protocol. Stop and wait protocol we are using. Second, we have a sliding window protocol, right? So this is the technique which is used for retransmitting the entire data unit when there is an error in the data. And second situation is that the receiver can use an error correcting code which automatically corrects the certain error. So today we are having the discussion on this particular technique, that how the error can be detected and how the error can be corrected. But in this lecture, we are going to have a single bit error detecting and error correcting code there. So the error correcting and error detecting code which we are going to use here is the Hamming code over here. Is the Hamming code. So Hamming code is an error detection and error correction technique used in digital communication and computer memory. It adds redundant parity bits to data bits to detect and correct single bit errors. So one thing you have to keep in mind, whenever we are going to detect and correct the errors we have to add some redundancy. Okay, we have to add some redundancy to the data. That means actual data will be sent with extra information or extra bit there. Extra information or extra bit there. This extra information or extra bit is called redundant bits there. These are called redundant bits. These bits are useful in error detecting and error correcting the data there. Now, how the Hamming code can be used to find a single bit error and how it can be corrected there. So to correct an error, the receiver reverse the value of the altered bit. That is, either 1 will be changed to 0 or 0 will be changed to 1 there. To do so, it must know the bit is in error there. So only how the receiver is going to change the particular bit where there is a change. First of all, it has to detect that particular bit where there is an error, and then that bit can be changed from 1 to 0 or from 0 to 1 there. But what is needed? The needed is that there is an error and at which position of the data there is an error. So the number of redundancy bits needed is, let's we have a data bits with m number of length. We have a data bits which we are going to add in this particular data bits, that is r. So total message which we are going to send is m plus r there. Okay, so the value of r must satisfy the following relation, that is 2 to the power r, which should be greater than equals to m plus r plus 1 there. Now let us suppose we have m equals to 4. Okay, that is the length of the data bits is 4. So we have to add some redundancy to it. So we are going to have the value of r, that how many bits we should add this particular value of data bits there. So we will follow this particular condition which is going to tell us the value of r there. So the condition must be like this: 2 to the power r greater than equals to 4 plus r plus 1. So we are going to put the values of r in this. So if r is equals to 1, then the condition will be like, let me erase this. So we are having this particular thing over here. We have m equals to 4. We have m equals to, the value of m is equals to 4. We are going to find out the value of r. So the condition will be 2 to the power r greater than equals to 4 plus r plus 1. Okay. So if we are going to take the value of r equals to 1, then 2 greater than equals to 4 plus 1 plus 1. That is 2 is greater than equals to 4. That is 5 plus 6. The condition becomes false there. Okay. Now we will take another value of r. So if we are going to take the value of r equals to 2, then we will see. So by taking the value of r equals to 2, 2 to the power 2 greater than equals to 4 plus 2 plus 1, that is 4 greater than equals to 7. Again, this condition is false. So we cannot take also this value of r, that is equals to 2. Now we will see the value of r equals to 3, whether it's satisfied or not. So the value of r equals to 3 will give us 2 to the power 3 greater than equals to 4 plus 3 plus 1. So that comes out to be 8 greater than equals to 4 plus 3 plus 7 plus 1, 8. So this condition is fulfilled over here. This particular inequality is valid. So the value of R is going to be 3 there. So the total length, the total message length, which we are going to now send is 4 plus 3, that is equals to 7. Total 7 bits will be sent in this particular message from the sender to the receiver. So you have to keep this in mind. The value of R must follow this condition. This condition, that is 2 to the power R greater than equals to m plus R plus 1 there. Okay. Now this is the particular data bits which we are going to use. The length of this data bit is m, and to this data bits we are going to add the redundancy bits there, that is R. So the total length of the message which we are going to be sent is m plus R bits. Now the question is that where to add these R bits to the data bits. So whether it should be appended in the back side of the data, or whether it should be appended in the front side of the data, or whether it should be added in between the data bits there. So in the Hamming codes, these redundancy bits are added in between the data bits there. Keep this in mind. We are going to add the redundancy in between the data bits. Okay, in between the data bits, and these bits will be at some position, right? So we will look on that, how to add these bits to the data bits, and at which position how many number of bits will come there. So this is the particular Hamming code. Okay, this is the particular Hamming code. We are taking an example of, that is, there are total number of data bits. Data bits in this particular case is, that is m equals to, now you will see 1, 1, 2, 3, 4, 5, 6, and 7. So total bits of data is 7. And if we follow the inequality to find out the value of R, then 2 to the power R should be greater than equals to m plus R plus 1 there. So the value of R will be equals to 2 to the power greater than equals to 7 plus R plus 1. So we want to prove this validity, that is 2 to the power must be greater than equals to 7 plus R plus 1. So for that, we are going to take the value of R equals to 4. So 2 to the power 4 should be greater than equals to 7 plus 4 plus 1, that is 16, greater than equals to 7 plus 4 plus 1, 11, 12. So the equality is valid. So we are going to have the redundancy bits, total redundancy bits, that is equals to 4. Now you see over here, in this particular redundancy bits, the position where we are going to add this redundancy bit, because the total length of the data which is to be sent, okay, the message sent will be equals to 7 plus 4, total 11 bits. So where to add these 4 redundancy bits in the 11 bits there? So these are added at bit number position 1, bit number position 2, okay, bit number position 4, and bit position number 8. So how we are adding that we will discuss. So in this particular Hamming code, we are adding the data in between the data bits there. So the redundant bits are added in between the data there. Now, where to add these particular bits? Okay, so let us see this with an example. The value of this particular R1. So now see, here we have R1, R2, R3, and R4 in this example. So how to, where the topic of discussion is that at which position we have to add redundancy bits. Okay, we are talking about this thing. Okay, at which position we are going to add. So the value of R1, okay, R1 is going to be added with the help of powers of 2 there. Okay, so we are going to add at the position 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3 there. Okay, how we are going to add the redundancy bit in the data? That is on the basis of power of 2. Okay, so the value, that is the redundancy bit R1, is added at the position 2 to the power 0, which is equals to 1 there. So it is added at the bit number 1 there. Then the position of R2 bit, the position of R2 bit, R2 bit is equals to 2 to the power 1. So that is equals to bit number position 2 there. Okay. So we are adding this value at position number 2 there. Then how we are going to add the particular third bit? Third bit is added 2 to the power 3, oh sorry, 2 to the power 2 equals to, that is equals to at bit number position 4. So the value of R is added at bit number position 4 there. Okay. Then we have the last bit, that is the fourth bit. The fourth bit is added at position number on the basis of 2 to the power 3 equals to 8. Okay. So at the eighth position, we are going to have this particular bit there. So what we have seen, we have data bits, D1, D2, D3, D4, D5, D6, and D7. These are data bits. To these data bits, we are going to add redundancy bits. The redundancy bits are, total redundancy bits are 4. These are the redundancy bits. So at which position we are adding? The R1 is added at position number 1. R2 is added at position number 2. Then the third R3 bit. Okay, third bit. Okay, in this case, we are writing at R4 because we are adding at the fourth position. And then the fourth bit is added at the eighth position. That's why we have written R8 there. These are the position where we are adding these bits. So total 4 bits are there. So in the message length, total message which is going to be sent is 11. We are sending the 11 bits, and the 11 bits, these all are the position. Okay, these are the position of the particular bits there. Okay, now see over here what is there. This is the position number. This is the position number. This is the position number 1. Okay, this is the position number 1. Sorry, this is the position number 1 because 2 to the power 0. This is position number 2 because 2 to the power 1. This is position number 2 because 2 to the power 2. And this is position number 3. That is 2 to the power 3 there. Okay. So that's why it is at the first bit, at the second bit, at the fourth bit, and third bit, and this is at the position number 8 there. These all are the redundancy bits over here. Okay. So in this way, we are going to have the positions there. Now, let us see this example, how to find out the value of R1. So first of all, we have discussed about the positions. The position is done with the help of the powers of 2, that is 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3 there. Then we are seeing to add these bits where in the total message there. So these are done with the help of power of 2. Okay. Now, what we are seeing over here, we are going to have, let me erase this first of all. Okay, now we are discussing that what will be the position of R1 is now, we know that, but what will be the value of R1, what will be the value of R2, what will be the value of R4, and what will be the value of R8 there. We are going to have a discussion. So the value, the value of R1, we are going to find out with the help of bits 1, 3, 5, 7, 9, and 11. Okay. By these bits, we are going to find out the value of R1. Why we are taking only these values 1, 3, 5, 7, 9, and 11? Because when you will see these binary codes, all these numbers 1, 3, 5, 7, 9, and 11 are having 1 at position 1 only. See, this is the 1 at position 1 in the binary value of 1. This is the position of 1 in binary value of 3. This is the position of 1 in binary value of 5. This is the position number of 1 in binary value of 7, and so on. In 9, we are also having this bit 1, first bit, and in the 11th, this is also going to be have first bit, because so the concept that the position of R1 is 1. That's why we are seeing only those binary values in which the position of 1 is 1 there. Okay. So in this all binary numbers, their position of 1 is 1. That's why to find out the value of R1, we will consider only these bits 1, 3, 5, 7, 9, and 11. Similarly, to find out the value of R2, now we are going to find out the value of R2. So R2 is at position number 2. So R2 is at position 2 there. So what we are going to show, we are going to see those binary numbers in which the position of 1 in their binary value is 2 there. So in binary value 2, we have the 1 at bit number position 1 there. Okay. See here, 2 is written as 0, 0, 1, 0. So it is here. Then we have 3. In 3, we have this 1 over here at bit number 2 there. Then at binary value of 6. So 0, 1, 1, 0. This is at second. Then we have binary number 7. That is 0, 1, 1, 1. Again, we have at bit position second. Then we have 10. At 10, the binary code of 10 is 1010. So that is at bit number position 10. Then we have 11. The binary code of 11 is 1011. Again, these. So for the value of R2, we are going to have bits which are going to give us the value, that is 2, 3, 6, 7, 10, and 11. Okay. Similarly, for R4, let me use this. So value of R4. So R4 is at position number 4 there, at position 4. So what we are seeing? We are seeing those binary values which are having 1 at, that is at third number. Okay, because this is the third bit. Okay, so R4 is the third bit. That's why we are going to have those binary numbers in which the position of 1 is at third bit there. So let us see 4, 0, 1, 0, 0. Here, the value of 1 is at third position. That's why we are seeing it. Then we have 5, 0, 1, 0, 1. Then we have 6, 0, 1, 1, 0. Then we have 7. In 7, we have 1, 0, 1, 1. In all the cases, there is a 1 at position number 3 there. Okay, position number 3 there. That's why the value of R4 will be find out with the help of 4, 5, 6, and 7. Now see, this is at position 4. Okay, this is at position 4th in the message, but this is the third bit of the redundancy. So we are going to see the third bit. Okay, now let us come to the value of R8. The position of R8 in the messages at in the messages at 8th, but this is the fourth bit of redundancy. So we are going to consider only those binary values in which the value of 1 is at position 4 there. Okay, let us see here. Binary value of 8 is having 1 over here. The binary value of 9 is having the value of 1 at this position. The binary value of 10 is going to have a 1 at this position. And the binary value of 11 is going to have a 1 at this position. So in all these cases, let me show you. In all these cases, that is at 8th, we have 1 triple 0. At 9, 1 0 0 1, and 10, 1 0 0 1, 11, we have 1 0 1 1. So see, all these position of 1 is at 4th. Okay, and what we are looking for? We are looking for the fourth bit of redundancy, fourth bit of redundancy, which is at position 8th of data. Okay, that is. Now let us see with this this thing with an example here. We have a data. Okay, we have a data that is 1 0 0 1 1 0. This is the data. Okay, so these are total bits D1, D2, D3, D4, D5, D6, and D7. So total value of M is equals to 7. Now we have to find out the value of R. So how the value of R will be found out? The value of R will be found out with the help of the inequality, that is 2 to the power R greater than equals to M plus R plus 1 there. So 2 to the power R greater than equals to 7 plus R plus 1. So we are going to have the value of 1, R equals to 1. So R equals to 1 will give us 2 greater than equals to, when we are going to put value of R1 equals to, that is 9 will come. This inequality is false. Then we will see with the help of 2 to the power 2 is equals to 4. 4 greater than equals to 7 plus 4 plus 1, that is total 12, 9. 7 plus 2, 8, 9, and 10. Okay, again this inequality is false. Then we are going to have the value of R equals to 3. So 2 to the power 3 is 8. 8 greater than equals to 7 plus 3 plus 1, 10 plus 1, 11. Again this inequality is false. So now the the value of R equals to 4. That is going to give us 2 to the power 4 equals to 16, which is 7 plus 4 plus 1, that is 16 greater than equals to 12. This inequality is true there. So we are going to add four redundant bits. Okay. Now these four redundant bits, that is, these are 1, 2, 3, and 4. Okay. 1, 2, 3, and 4. Okay. That is going to be add at the position of 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3 there. Okay, 2 to the power 1 is 1, 2 to the power 2, 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, and 2 to the power 3 is 8. So we are going to add the first bit at position number 1, second bit at position number 2, third bit at position number 4, and fourth bit at position number 8. Okay, so here are the values of R at position number 1, R at position number of 2, R at position number 4th, and R at position number 8th. Okay, so this is the position of the redundancy bits. Now we are adding the suffix. This is R1, this is R2, this is R4, and this is R8 there. Okay, these are the four redundancy bits which we are going to add in the data in between there. Okay, now we have to find out the value of R. Okay, all these positions, the value of all these positions, how we are going to find out? First of all, we have to consider that in this example, we are taking parity to be equals to even. Okay, parity equals to even. That means sender and receiver will look only for the even number of ones in the particular code there. Okay, that is. So how we are going to find out the value of these positions? So first of all, we are finding the position of this R1. Okay, the value of this R1. Okay, let us see now how this value of R1 is found out. So for this R1, what we are doing? We are considering those binary values, which are having one at first position. Okay, one at first position. So look, let us look. This is binary value 1. This is 3. So 1, 3, 5. Okay, 7, 9, and 11. So we are seeing 1. So 1 in 4 bits, 0, 0, 0, 1. Why we are taking 4 binary bits? Because total message length is 11. Okay, that's why. Then we have 3, 0, 0, 1, 1. Then we have 5, binary value of 5. That is 0, 1, 0, 1. Then we have 7, 0, 1, 1, 1. Then we have 9. 9 is having 0, sorry, 1, 0. 1, 0, 0, 1 there. Then we have 11. 11 is having 1, 0, 1, 1. So all on these binary codes, we have 1 at position number first there. That's why we are considering these all values. Now let us see that at 3, we have 1 because there is a data bit. Then we have 5. The value is equals to 0. Okay, these are the data bits. Okay, the value of fifth bit is 0. The value of 7th bit is 1. The value of 9th bit is 0. The value of 11th bit is 1 there. Okay, so total number of 1 at this position, 1, 2, 3. Okay, we have total number of ones, 3. Now what will the value of this redundancy bits? This redundancy bit will be equals to 1 there. Because why? Because we want an even parity there. Okay, so the value of R1 How we have find out? We have find out with the help of 11th bit, with the help of ninth bit, with the help of 7th bit, with the help of 5th bit, with the help of 3rd bit. Okay, these values are 1, ninth is having value 0, 7th is having value 1, 5th is having 0, 3rd is having 1. So total number of ones are 3. So the R1 is going to be 1, which is going to give us even parity rate. Okay. Similarly, now let us look how to find out the value of second redundancy bit there. Second redundancy bit, now we are considering here this R2. So we are finding the value of R2 there. So for R2, let us see how we are going to find out the value of R2. So R2 is at position number 2 of original of the transmitted data. Okay. So we are going to see all those binary values, all those binary, all those binary values which are having one at position 2. Okay. So those values are 2, 3, 6, 7, 10, and 11, because all these decimal numbers are having 1 at position number 2. Let us see 0, 0, 1, 0, 3, 0, 0, 1, 1. Okay. 6, 0, 1, 1, 0, 7, 0, 1, 1, 1, 10, 1, 0, 1, 0, 11, 1, 0, 1, 0, 1, 1. All these are having 1 at position number 2 there. So how to find out the value of these? So the value at position number 2 is equals to 0. Okay. Sorry, not 0. The value of this we have to find out at position number 2. We have to find out because there has to be R2 there. Okay. Now the value at position number 3 is 1. The value at position number 6 is 1. The value at position number 7 is 1. The value of position number 10 is 0. And the value at position number 11 is 1. So total ones are 1, 2, 3, and 4. Now look over here. 1, 2, 3, and 4. So already there is an even number of ones. So the value of R2 is going to be equals to 0 there. Okay. So that's why the value of R2 is 0. Right. Similarly, we are going to have the value of R4 and R8. Now let us look all this. So now we are going to find out the value of R4 because it is at position number 4. Okay. That is third redundant bit. So we are now finding the value of third redundant bit, which is at position fourth of the transmitted message, right? So for finding out the value of R4, find the value of R4, we have to see those binary, those binary numbers, those binary numbers which are having 1 at position third. Okay, why third? Because this bit, this R4 bit, this R4 bit is the third redundant bit, okay, which is at position 4 of the transmitted message. So the values are, the binary values are, which we are going to see is that is uh, fourth, binary value fourth, 0 1 0 0, 5 0 1 0 1. Then we have 6 also, 0 1 1 0. Then we have 7 also, 0 1 1 1. Then we have uh, uh, that is these. Okay, all these are 4 5 6 and 7. Okay, that is this one. So fourth, this is fourth, 5 6 and 7 there. All these values we are going to consider there. So these are having 1 at position number 3. So now the value at position number 5 of the transmitted message is 0. The value of position number 6 is 1, and the value of position number 7 is 1. So we have total number of ones equals to 2. Position number of 1, total number of ones is equals to 2. We have even parity. That's why the value of R4 is going to be 0. Okay, this is the value of R4. Now, the last redundant bit is at position number 8th. This is R8 at 8th position, and this is the fourth redundant bit. Okay, fourth redundant bit at position 8th of transmitted message. Okay, transmitted message. Now, how to find out the value? As this is the fourth redundant bit, so we are going to check every binary number which is having 1 at position number 4th, and those binary numbers are 8, 9, 10 and 11, because the binary code of 8 is 1000 1001. 10 is having 1010, and 11 is having 1011. So all these are having binary value of 1 at position number 4 there. But at 8th, what is there? There is R8. At 9th bit, there is the value 0. At 10th, there is a value 0. And at 11th, there is value 1 there. So see here, here we have R8. Here we have, this is 9th bit, this is 10th, and this is 11th bit. The 9th bit is having value 0, 10th bit is having value 0, and 11th bit is having value 1. So total number of ones is odd. That's why the value of R8 is 1 there. Okay. So in this way, we have find out all the values of R1, which is equals to 1, R2, which is equals to 0, R4, which is equals to 0, and R8, which is equals to 1. So the original message now will be, which we have to transmit, that is of total 11 bits, and the message is 1 0 0 1 1 0 0 1 0 1 there. Okay, this is the thing there. This is the code which we are going to send. Okay, in this way we are going to have the values of R1, R2, R4, and R8. Now, what we are doing, the sent messages, this one, we have going to send this message. Now, when sending, there can be an error. So we are looking for how the Hamming code will find out the single bit error and how we can correct it there. So what we have done, we have made an error in this particular bit here. This one has been converted into 0. So the received bit is 10010101001. But how the machine will come to know that there is an error in the particular data, and how it is going to find out at which position there is an error in the data there. So we are going to again see that how to find out this particular thing. So look over here. These are the 11 bit. So these are the received bit. Okay. These are the received bit. Okay. So the received bits are 10010100101 there. So again, we are going to now check. First of all, we are going to check all the values. Okay. So what we have to check? We have to check the values of R1, R2, R4, and R8. We are going to check all those values there. So how to check it? How to check? Because we know the position of R1 is at position number 1 of the transmit of the receive message. The value of R2 is at position number 2 of the receive message. The value of R4 is at the position number 4 of the receive message, and the value of R8 is at the position number of at the position 8 of the received message. So we are going to check it. So we know that for R1, we check the bit position 1, 3, okay, 1, 3, 5, 7, 9, and 11, right? We see all these bits 1, 3, 5, 7, 9, and 11 there. So the value at position number 1 is, this is the value at position number 1 is 1 there. The value at position number 3 is 1. At 1 it is 1. At 3 it is 1. At 5th it is 0. At 7th it is 0. At 9th it is 0. And at 11 it is 0 there. Okay. So total number of ones are 1, 1, 2, and 3. So there is an odd parity. What we have to do? We have to make it an even parity. So now the value of this check value, the check value will come out to be C1 equals to 1 there. Okay. Similarly, for checking the value of R2, we have to consider the position number 2. We are going to check position number 2. We are going to check position number 3. We are going to check position number 6, 7, 10, and 11. Why? Because all these are having 1 at position number 2 there. So now see over here, at position 2, we have binary bit 0. At position 3, we have binary bit 3. At 6, we have binary value 1, 0 at 7th position, 0 at 10th position, and 1 at 11th position there. So total number of ones 1, 2, 3. So the check value comes out to be 3, and we want what we want? We want an even parity. So the value of C2 will come out to be 1 there. Okay, C2 will come out to be 1 there. Okay, now we are going to check the value of third redundant bit, which is at position number 4 there. So for that, we are going to see the values of the received message 4th, 5th, 6th, and 7th, because all these numbers are having 1 at position number 3 there. So these values are 0, 0, 1, and 0. So there is an odd number of parity. again the value of check C3 will be going to be 1 because we want to make it even. Okay. Now the last value which we are going to check is for the R8. Okay. So because R8 is the fourth redundant bit, so we are going to look on those binary numbers which are having 1 at position 4 there. Those are 8, 9, 10, and 11. Okay. So this is there. So that is the value 1, 0, 0, 1. So there is an even parity. That's why the value of check is C4, that is equals to 0. So the values of C1, the value of C1, C2, C3, C4 is come out to be 0, 1, 1, 1. That is equals to binary value 7, decimal value 7. So at seventh position there is an error. Okay, at seventh position there is an error. So now look, 1, 1, 2, 3, 4, 5, 6, and 7. That means at seventh position there was an error. So the receive bit was 0. The receiver will change this value from 0 to 1 there, and the original message will be recreated. That is 100 1 1 1 00 10 1 there. So in this way, we are going to have an particular error correction there. Okay. So this is the way how we are going to find out the value there. So in this way, we see how the Hamming code is used to detect a single bit error through the with an example. Uh, Always remember that the values of redundancy bits are going to be at the position of powers of 2 there. Okay. And in this way, we are going to find out the error there. So the conclusion of this particular lecture is that Hamming code is a powerful error detection and error correction technique that enhances data reliability in digital communication and computing. By using redundancy parity bits, it can detect and correct single bit error, ensuring accurate data transmission. The technique is widely used in computer memory, networking, and satellite communication, where error-free data transmission is critical. Understanding Hamming code provides a strong foundation for learning more advanced error correction methods like Reed, Solomon, and BCH codes there. In summary, Hamming code improves data integrity, reduces transmission errors and errors, ensures efficient communication in digital system. So today what we have looked on the error correction method, that is Hamming code there. The books which you can refer is Crows, Tannenbaum, and Frozen. Thank you. Thank you.